Hey everyone, welcome back again, and thank you for joining us as we open up the discussion of counting techniques. Well, heading into our first objective, we're going to discuss solving counting problems using the fundamental multiplication rule. This is as fundamental as it gets. We're going to jump right into an example to explain this using some logic before we get a little mathematical. We're told a restaurant offers a special that includes the choice of one appetizer, one entree, and one dessert. There are 2 appetizers, 4 choices for entrees, and 2 choices for dessert altogether. So, how many different meals can be ordered? We like this type of question because this is what a lot of marketing ideas use. Different restaurants will advertise how many different meals you can get, and it's really just a manipulation of specific items within each meal. Well, looking one more time at our options, we have 2 choices for appetizers, 4 different entrees, and 2 different desserts. In order to find how many different meals we can get, we simply multiply our options. That is, we just read that we have 2 choices for an appetizer, 4 different choices for entrees, and 2 different desserts that we can choose from. If we multiply these results together, we end up with 16 different meals that we can order, and we find that using the fundamental multiplication rule with these counting techniques. Now, to create a little emphasis here, notice that the question is asking how many different meals that we can be ordered. We're trying to make sure we keep this separate from our probability questions here. They're not asking us what is the probability of this, that, and another. That's how we know it's a different multiplication rule. It's a multiplication rule as applied to counting problems. Or the question is, how many different ways can something occur? Just to add one more layer a little visually here. One more time, we were told we have 2 choices for an appetizer. So let's say those 2 choices were soup and salad. The reason why we multiply is it is a sequence of decisions, and that's the phrase we haven't said yet, but it's a sequence of decisions that leads us into this thought process. If we start with soup, then that means we have 4 different options for those entrees. After we choose our entree, we have 2 options of desserts. Well, that means for our 4 different options of our entree that is discussed, we have 2 options of the desserts that lead to 2 different meals. That means we have 2 meals going on here that apply to 1 appetizer, 1 choice of entree, and then 2 different desserts. As we choose one, it leads to 1 meal. Altogether, that means we end up with our 16 meals here, but that's because our sequence of decision creates options within options. As a result, we can just multiply those options like we showed with that multiplication rule, and that's how we get to our 16 different meals. Well, hoping that's okay for our starter, let's go ahead and jump into the next quick example. Oregon University football is known for its multiple uniform combinations. They have 5 different styles of helmets, 12 different jersey styles, and 6 different pant styles, along with 4 different styles of cleats, which are just shoes for those who don't know football. How many different uniforms can Oregon wear if we're factoring in these items? Well, just like the previous example, we have 4 different categories working with here: helmets, jerseys, pants, and cleats. And again, we have a sequence of choices, meaning we're going to choose our helmet first, then our jerseys, then our pants, then our cleats, or any other order. But the idea is, since it's a sequence of choices, we're using yet again the multiplication rule of counting. Just to emphasize one more time, notice the question is, how many different uniforms can Oregon wear? Not a question of probability. If we're okay with that, we were told that we have 5 different styles of helmets to wear, 12 different jerseys that we can choose from, 6 different pants, and 4 different cleats that we can choose from. Multiplying all those one more time, just like we did previously, we end up with 1,440 different uniforms that we can wear as an Oregon University football player. And that means we're all set using our multiplication rule of counting. However, that does beg the question, what is the multiplication rule of counting? Well, the multiplication rule of counting is the total number of possible outcomes. Just to say that one more time, it's the total number of possible outcomes. Again, we're not finding a probability right now. That tends to be confused when it comes to exam time. It's the total number of possible outcomes from a series of decisions where we're making selections from different categories we found by multiplying the number of choices for each category, like we did in the examples. Mentally, we make a slot for each decision, enter the number of choices for each decision in the slot, and multiply those numbers together to get our result. Well, that takes us to our next objective then, where we're going to solve counting problems now using permutations. Well, to define a permutation, that's an arrangement in which R objects are chosen from N objects, such that the N objects are distinct, repetition of these objects is not allowed, and order is important here. Let's draw a little emphasis towards that order aspect, because later we're going to discuss combinations, and order is the distinguishing piece between permutation and combinations. But we'll explain that, of course, with some examples. The idea behind working with permutations, though, is we want to go through this checklist where we have distinct objects with no repetition and order being specified and important. That way we know we're trying to find a permutation. On the math side, we need to make sure we realize we need to know this formula as well. If we're asked this on a free response question, we have to be able to replicate our formula and work through the math by hand to show that we understand the math behind the scenes. Just to draw some emphasis at the moment, notice that this notation is n factorial. That exclamation point means factorial. It's not like a real excited n. Instead, it's n factorial divided by our quantity n minus r factorial, and we will elaborate a little more on this with our examples as well. Let's head into this first example then. We're told we need to select a new president, vice president, and secretary for the Dodgeball Hall of Fame Selection Committee. There are 15 people on the committee to choose from. In how many ways, and I'm going to pause there and highlight that again, in how many ways can the three positions be selected? So again, trying to create that emphasis, we're not asked a probability question here. Instead, it's this idea of counting, but now we have to figure out, is it just multiplication rule of counting, or are we working with permutations? That means we need to go through our checklist in order to address that it is a permutation. We start out with the fact that people are distinct. We are selecting people from this committee, therefore, we know we're working with distinct objects. Next, there's no repetition because we have to select the president, vice president, and secretary. We're not going to have one person acting in two roles, like one person being both the president and vice president. Instead, there's going to be one person for each position, thus no repetition. And lastly, sometimes it's a little bit sneaky, but order matters here. The reason why order matters is because there's a rank involved with our selection. You may want to make a note to yourself that when we say order matters, rank is involved as well. Those go hand in hand. Rank makes a difference. Since we're selecting a president, vice president, and secretary, that's what allows us to know that order matters, and thus we're working with permutations. If we're all set there, then that means we get to go back to our permutations formula to actually find our result. Well, we have our formula. We just need to address what n and r need to be specifically. That is, we know we're finding an NPR. We were told we have 15 people on the committee to choose from. That means n is 15, meaning the total number of people that we have to choose from. And since we have 3 positions to be selected, that means r would be 3. If we're okay with our substitution, then that means we're all set. We get to go into the formula. That means we have 15 factorial divided by our quantity, 15 minus 3 factorial, substituting our values for n and r, just based on the formula that we have for NPR. And if we're okay with that substitution, that means we're trying to find a 15 factorial divided by the 12 factorial. Now it depends on how much your instructor asks you to show. We're going to go ahead and show the full breakdown here and how we simplify this to get our final result. Well, the definition of factorial would be the value of 15 being multiplied by each integer going from 15 down to 1. That is, we have 15 times 14 times 13 all the way down to 1. That is the definition of factorial. Now we have 15 factorial divided by 12 factorial, and that means 12 factorial would go from 12 times 11 times 10 all the way down to 1 as well. I've arranged it like you see though, because that means we're going to have a lot of repeated factors that are just going to cancel out for us. That is, we can see that 12 over 12 would reduce to just be 1, 11 over an 11, 10 over 10, etc., all the way down the list. Which means after we reduce all these factors, we have a result of simply 15 times 14 times 13. And that leads us to our result of 2,730 different ways we can select our 3 positions. And we're all set with our first permutation example. Let's pause for a minute though, because we want to tie this idea of permutations back to our multiplication rule for counting. The idea here is if we can recognize this as a sequence of decisions, we actually can go with our multiplication rule of counting as opposed to needing to use permutations. This is a little bit deeper than we absolutely need, but it's a great conversation. Our result came from the math where after we simplified, we had just 15 times 14 times 13. If we think of this in terms of a sequence of counting, we have 3 different people that we need to select: the president, vice president, and secretary. Well, if we have 15 people to choose from, then that first person that we choose, let's say we're choosing the president first, we have 15 people available to choose as president. After that person is selected, we have only 14 people left to fill the other two positions. Well, that means if we're choosing vice president next, we have 14 people to choose from. Once we have that person chosen, we need to choose a secretary, and there are 13 people left to choose from, just like if we were working with appetizers, then entrees, then desserts. So either way, we can go the route of permutations, or we can recognize that a sequence of decision exists here, and we could have used the multiplication rule of counting. If we're all set there, let's head into our next example then. This one has us discussing the idea of a trifecta. In horse racing, the trifecta bet is when a person bets on what horses will finish first, second, and third. So you're not just betting on a winner, you're saying I think this horse will win, this horse will finish second, and this horse will finish third. The bet has a good payout, but it's difficult to be correct because you have to choose correctly all three horses that finishes in the top three and the correct place for each horse. There is something called a trifecta box in case you want to sound fancy talking about horse racing, but we'll talk about that another day. Instead, our actual question has us saying, in how many ways can horses in a 10-horse race finish first, second, and third? Again, the emphasis on the question, we're asked how many ways, not a probability question, but instead we know we're working with counting techniques. Well, let's go through our checklist again to see what we're working with. Just like in our previous example, people are distinct, just like horses are distinct. And if you disagree and you've never seen horse races, they literally throw numbers on the side of those horses so that you know who to cheer for as you bet your trifecta to win your money. If that's okay with you, the next aspect would be that we have no repetition. Last time I checked, I've never seen a horse race where a horse finishes first, backs up, and then finishes second also. Therefore, there's no repetition when it comes to this race. Once a horse finishes, he or she is done, and thus no repetition. And finally, since we're talking about a race, order does matter here. They don't hand out a lot of participation trophies for horse races, but emotionally we know they count. However, since rank matters, meaning there's a difference between finishing first and second and third, that means order does make a difference. Order does matter here because of that rank idea yet again, so we're working with a permutation. If we're comfortable with the fact that we're working with a permutation, that means we're talking in terms of this NPR yet again, n being 10, because we have 10 horses in this race. So we have 10 horses total. We're choosing how they finish first, second, and third, so we are choosing 3 horses, thus n is 10 and r is 3. If that's okay, applying that to our permutation formula, we have 10 factorial divided by our quantity 10 minus 3 factorial. As we expand out our factorial, I'm going to shorten up the work a little bit this time, in case your instructor says it's okay to do so. The idea here is, we know that 10 minus 3 is 7 factorial. So in our numerator, I've got 10 times 9 times 8 times 7, but I'm going to leave that as 7 factorial divided by the 7 factorial, again because 10 minus 3 giving us our 7, and that way we have 7 factorial here, and those two guys are going to cancel each other out because we know 7 factorial is the same as 7 factorial, so it's okay for us to leave this in the shorthanded version. That is, each of these factorials will expand out, causing all of their common factors to be reduced to 1. And that means we're just left with, one more time, 10 times 9 times 8. Tying in that idea of sequence of choices yet again. If we're talking about how 3 horses are going to finish a race and there are 10 horses total, then that means 10 horses have the chance to win the race. After that horse wins, we've got 9 horses that have a chance to finish second. After that horse finishes, that means we've got 8 more horses that can finish third. So we can use, one more time, the multiplication rule of counting to get our 720 different ways for these horses to finish this race. And we're all set one more time with another permutation question. So that takes us to our next objective then, where now we're working with counting problems using combinations as opposed to permutations. Well, a combination is yet again an arrangement in which r objects are chosen from n objects, such that, yet again, the n objects are distinct, repetition of the objects is not allowed, but this time order is not important. And again, that's our difference between combination and permutations. So let's make sure we draw some emphasis to that. The difference between permutation and combination. Combination, order does not matter, while permutation, order does matter. Taking a look at our formula, notice the notation is NCR now, as opposed to NPR. And we have yet again a factorial situation, but now we're dividing by r factorial as well in the denominator here, and that's going to lead us to smaller results since we have more factors in the denominator. Note one more time, we do need to be able to do this work by hand, just like we did with permutations, if this ends up on a free response question on an exam. Let's go ahead and jump into our example then. We're asked how many different simple random samples now. Again, emphasizing the question, not a probability question, but how many different simple random samples of size 4 can be obtained from a population who is size 20. So we didn't get very specific this time, not horses or people or anything. Instead, we're just talking about some sort of objects and we're trying to create a simple random sample. Well, based on our rules for simple random sample, we know these objects need to be distinct. We know that there's no repetition allowed in our simple random sample. And since it's an SRS, we know that order does not matter here. Since order does not matter, we know we're working with a combination as opposed to a permutation, and that heads us down the correct route. If we're okay with the analysis then, let's head over to our formula. We've addressed that it's a combination, so we have NCR that we're working with. We have a population of size 20, so N would be our 20. That is the number of objects that we're choosing from, and we have a simple random sample of size 4 that we're getting, therefore R is 4. Substituting that into our formula, this time we have n factorial over 4 factorial multiplied by our quantity 20 minus 4 factorial. That leads us to our little bit of simplification here. 20 factorial now divided by 4 factorial multiplied by 16 factorial still in the denominator. I'm going to break down the 20 factorial like we did previously, stopping at 16 factorial though. That way the 16 factorial in the numerator matches the 16 factorial in the denominator, because we know yet again these two items would create the same factors, all reducing to be 1, and instead we can just work with the remaining factors. That means we're left with 20 times 19 times 18 times 17, now divided by 4 times 3 times 2 times 1. We can throw this math into our calculator. If you do so, make sure you're careful using parentheses, or you can continue to reduce the fractions, all depending on what your instructor requires. But either way, the arithmetic leads us to our 4,845 different ways that we can choose these simple random samples. And we've got our first example using combinations now, focusing on the fact that order did not matter when we were selecting our groups. If we're all set there, let's go ahead and jump into our next example. We're told a state lottery is held drawing 6 numbers that range from 1 to 50. They tell us nice and straightforward here, the order in which the numbers are drawn does not matter, which of course is a big deal to us. And highlighting it one more time, the actual question itself is asking, in how many ways can the 6 numbers be drawn? Still not working with probabilities, instead we know we're working with counting. Well, bringing up our 3 criteria again, we know that numbers are distinct, that is, we can tell the difference between our numbers that range from 1 to 50. We know in a lottery that no repetition is allowed, meaning if they pull number 7, you know number 7's not coming up again, and they flat out told us that order does not matter, thus we're working yet again with a combination. Now since the numbers range from 1 to 50, that means we've got 50 different numbers to choose from, therefore n would be 50, and since we're choosing 6 numbers, we know 6 would be our value for r. As we address our NCR situation, we know we have a 50 choose 6 situation, and we can move yet again into our formula. That means we have 50 factorial over our 6 factorial multiplied by our quantity 50 minus the 6 factorial, or simplifying a little bit, our 50 factorial divided by our 6 factorial over our 44 factorial. Only because we've addressed it before already, we're going to go ahead and jump to our result, expanding our factorials a little bit up top like we've done previously, breaking down the 50 factorial until we get to our 44 factorial, since yet again we know these two factorials will wipe each other out, and that leads us down to our specific factors to reduce, and we end up with a result of 15,890,700 different ways that we can choose 6 numbers from a total of 50 numbers for this state lottery, which means we've solved our combination question one more time, and it also lets you know how good your chances are to win a state lottery. That takes us to the idea of finding permutations and combinations using our calculators now. Well, just bringing up a previous example where we talked about our 10-horse race and how the horses can finish in first, second, and third. Remember, we had 10 horses total, and we were picking 3 of them where order mattered, so we know we're working with a permutation already. Focusing on the calculator now, to find your NPR function, we're going to hit the math button, but before you do that, we first want to input the value of n into our calculator. That is, we're going to input the value of n, Then we're going to find our NPR function. Then we're going to input our value for r. Heading over to the calculator to explain. Remember our value for n was 10. It's only because of the way the calculator works that we input 10 first. Then you're heading over to the button that is Math. Arrow over to your option that says PRB. Mine says PROB because it's a little bit fancier apparently. When you see that, we have our option number 2 here. That would be NPR. When you hit NPR, now you're inputting the value for r, which we had was 3, meaning those horses finishing in the top 3. When you hit enter, you get your results of 720, just like we found by hand, and there's our NPR. Heading back over to the notes now, we know how to find NPR, so now let's go ahead and use the NCR function, meaning now we're trying to find a combination based on the problem. Our previous example discussed simple random samples. We had size 4 obtained from a population of 20. So just like we had with NPR, now we're going to use the NCR operation. We have a combination of 20 objects where we're choosing 4 at a time. So that means we have a 20 choose 4 situation like we found by hand. Just like we did with permutations though, the first thing we want to input is that value for n. So we're going to input 20, then find our NCR function before we input our value for r. Jumping back over to the calculator then, we just said our value for n was 20, so we input that. I'm going to hit the math button, arrow over to our PROB or PRB depending on your calculator, and we see option number 3 is NCR. We just used NPR, now again going NCR for the type of problem that asks us to find a combination. So we have 20 NCR, and we need to input that value for r, which we had 4. A 20 choose 4 is what we were trying to find, and that led us to our 4845, just like we found by hand. And that means we know how to find both permutations and combinations using our calculators. And thank you again for joining us.